Welcome to the APL quest. See APL Wiki for details. Today's quest is the 6th from the 2014 round of the APL problem solver competition. We are supposed to count the number of ways that you can throw any given result with a given set of dice. And so this isn't a statistics of what the chance is of getting a particular result, but just counting the number of ways. A very simple approach to this is exploiting the magnetic iota, or the index generator. So let's say we have two dice that have 6 dice, so those are normal dice. Then the indices in an array of that size, 6 by 6, contain all the different possibilities that the dice can show. And so this means that if we sum each one of these lists of face values, then we get all the sums. Then revealing that result gives it as a single list, and finally we can use key to summarize. We are not interested in the actual position here, we're interested in the count, so we take the particular value, concatenate it to its count, and apply that with key, and that gives us the result that we're looking for. We can give this a name. This uses index generation, so we can call it I, like this. However, it does have a problem besides for performance, which we'll come right back to, and that is that since it's generating an array of the given dimensions, where every element is the index of that element in the array, then it is subject to dialog APL's limitations in the sizing of arrays. And as it is today, dialog APL does not allow arrays that have more than 16 dimensions, rather more than 15 dimensions even. Indeed, if you need more than 15 dimensions, you might be doing something wrong, or at least a little bit odd. So if we try it, let's say we have two-sided dice. This actually means they're like coins, so the coin flips. That's all very good. So we can either have both of them showing a 1, or both of them showing a 2, or one of each, which means there are 2 possibilities. But let's say we have a bunch of coins. Let's say we have 15 coins. Then a lot of possibilities like this, and it's perfectly reasonable to throw then 16 coins as well. Problem is that we're not allowed to generate an array that has this rank, that has 16 dimensions. Furthermore, there's a problem of performance here as well, because we're generating a nested array with every element is a pointer, and because every element is in itself an array, not just a simple scalar. And that is a bit wasteful in representation and dealing with it. But we can achieve the same result in a not too complicated way. By observing that the number of elements in our resulting array, it is clearly, so in the 2-dimensional case, it's 6 by 6 when both of them are 6, and in general, it is the product of the dimensions along every axis. So all the possibilities is the product of the number of sides on all the dice. And then we have all these values, although we should start with 0, because we're going to use mixed radix representation here. And so let's just take it for 6 for now. And then so this gives us a long list up to 35. Now, if we then represent this in the radix of 6, 6, then every row represents the value of one die And so the first row is the first die, and the second row is the second die. And then we can get the sum. The only problem here is because we're counting up from 0 rather than from 1, we just need to increment again. And then we can go and sum vertically, and that gives us the total sum. So here we managed to do it without having nested arrays, just direct computation based on the mixed radix. In this case, it's the same radix, but it could be anything, of course. And then we can proceed as we did before by concatenating the value with how many times it appears using that for key, and we can call that E for encode, because we're using encode over here to generate all the values. And then we can try it with 16 coins, and that works just fine. It will also be nice to see, as I mentioned, there might be a problem with the performance of it because it's a nested array, whereas here we're dealing entirely with flat arrays. So let's compare that as well. We're copying in CMPX from the defense workspace. And then we need some test data. This is a little bit interesting. What kind of test data? There's no limit, of course. You can throw as many dice as you want, and they can have as many sides as you want. So we can try to make some variation of cases. So let's just start with small cases so we can see it, and then we can scale it up. So in fact, we can have a die that has no sides at all, in which case it doesn't really contribute, but we can still include it. So let's just start here with from 0 to 3. Oh, right. So we can have dice that have no sides, but they don't contribute. We can also have no dice at all, in which case the result obviously is 0, but we can include that here. So here's between 0 and 3 dice, and then for each one of them, we use that number to replicate the number of sides on a die. So here 3, just to keep it small. Okay, and that means we could also, for example, roll them like this. So these are dice rolls with 0, 1, 2, 3 dice that have 3 sides each. What we really want is we want all the possibilities, because maybe we have one die that has 2 sides and one has 3 sides, one has 1 side. And then we can do it like this. So this gives us a grand table of with 0, 1, 2, and 3, and then all the different die sizes. So we can then combine all of these into a single list. So we can do a concatenation reduction over this list of multidimensional arrays. We need to flatten each one before we do that, and then disclose because we had reduced them, and that gives us our giant list of die hands that we can then throw. And now let's scale this up a bit, and there's not really any given limit to this, so I'll just say between 0 and 4 dice, and the dice can have up to 9 sides each. And these are our test cases. Let's count how many test cases we've got. We've got 7,000 something test cases. That seems well enough. Okay, so CMPX, and then we have I for the one that used IOTA to generate the indices on each one of these test cases, and then we had E, which was the one that used encode on each one of these test cases. Oops, did I make a mistake here? Oh yes, of course. There's a mistake in our definition of E, and that is because I forgot to ravel here. The problem is that we can be given the argument as a single number as well, and then we're going to missing out on the rank. So we need to make sure that the left argument to encode is also a vector. We can do it like this, or we could use the over operator to make sure to ravel both. The right argument is always going to be a vector anyway, because we get it from IOTA. So let's try that again. And we can see that avoiding the nested arrays can give us some significant speed up there. But there's actually more we can do, and that is looking at key. So for key, here we used a tacit left operand. And there are some special cases, and this is exactly one of them, where we want the value concatenated with its count, and that has been highly optimized if you state the operand as a defen. So left argument concatenated with the tally of the right argument instead of that. And this seems like a very small difference, but this is the defen inner key. And then we can compare the performance of E and ED. We should see a significant performance improvement there too. There we go. So playing around a little bit and trying out the operands for key can actually make a big difference. And there are some combinations that have been special cased and run much faster. Thank you for watching.